All right, let's jump right in. What if I told you that to solve some of the most insanely complex problems out there, you don't need perfect, clean formulas? What if the secret ingredient was just randomness? I know, it sounds kind of nuts, right? But that's the whole idea behind these things called Monte Carlo methods. So to get a feel for how this actually works, we're going to start with a really simple problem. But here's the thing, it's surprisingly hard to solve with the kind of math you probably learned in school. Take a look at this. I mean, what even is that? It's a blob. There's no neat little formula for the area of this thing. So how would you do it? Seriously, take a second. How would you even start? Okay, you ready for this? The answer is, well, it's not what you'd expect. Instead of trying to measure it with a ruler, we're actually going to embrace the chaos. And here's the really cool part. The solution is so simple, it's kind of beautiful. We just draw a simple square around our weird shape. Then we just start throwing thousands of random darts at the square. And all we have to do is count how many landed inside the blob versus how many landed outside. That simple ratio, that gives us a shockingly good estimate of the blob's actual area. And that right there, that's the whole magic trick behind Monte Carlo methods. You're just using a whole bunch of random simulations, a computer throwing darts for you, to get a pretty good estimate of something that's way too hard to calculate perfectly. It's like taking a poll to understand a whole country. Okay, so let's take this idea a step further. We can use this exact same dart-throwing logic to tackle a classic problem from math class, finding the area under a curve. You might remember it as integration. Now, if you remember your calculus class, the traditional way is super orderly. You slice the area up into these perfect, tiny little rectangles and add them all up. But Monte Carlo? Nah. It's just like our dartboard. It just throws a whole cloud of random points at the graph and counts how many fall under the line. It's pure chaos versus pure order. So how on earth does that chaos give us a real answer? Well, the trick is to stop thinking about it as a single calculation. Instead, what we're really doing is estimating the average result you'd get if you could throw an infinite number of darts. In stats, they call that the expected value. And the reason we know this works, the reason it's not just guessing, comes down to this really fundamental idea in statistics called the law of large numbers. All it says is the more you do something, the more darts you throw, the closer your average result is going to get to the true actual answer. So believe it or not, more randomness actually leads to more accuracy. All right, finding areas is cool and all, but this idea is so much bigger than just geometry. We can also use it to peek into the future, to estimate the chances of something happening. Let's say, for example, you've created a new medical test. You need to know how powerful it is. Basically, how good is it at catching a disease when someone actually has it? Trying to figure that out with a formula can get really, really messy. So forget the complicated math. We just simulate it. We tell a computer to generate thousands of fake patient results. Then we run our new test on every single one of those fake patients and just count. How many times did it work? That percentage, the success rate in our simulation, ends up being an amazing estimate of how powerful the test will be in the real world. And check this out. This chart shows you exactly what we're talking about. See, with only 25 simulations, our estimate is, it's a bit off. But just by bumping it up to 100 simulations, bam, we get way, way closer to the real answer. It's the law of large numbers in action. More samples, better answer. Simple. Okay, so up until now, we've been throwing our random darts at targets we could, at least see. But what if the thing you're trying to measure is a total mystery? What if you need to map a landscape that's completely invisible? This is where things get really wild. Think about trying to map a mountain range, but in total darkness. You don't have a map. The shape of the mountains is the very thing you're trying to figure out. How do you throw darts at a target you can't even see? Well, the answer is this incredible technique called Markov chain Monte Carlo, or MCMC. And the best way to think about it is like one of those robot vacuums mapping your house for the first time. It can't see the whole room. It just takes a little step, senses what's around it, takes another step, and over time, it builds a pretty good map of where it can and can't go. It's a random but smart walk. So here's how that smart walk works. It starts somewhere random. It takes a random step to a new spot. If that new spot is better, say a higher point on our invisible mountain, it almost always moves there. But here's the absolute genius move. Every now and then, it will intentionally take a step to a worse spot. Now, why would it do that? Well, that's what keeps it from getting stuck on the very first hill it finds and forces it to explore the whole mountain range. And when you get it right, this is what it looks like. This plot is basically the trail our little random walker left behind. See how it's jumping back and forth between those two big peaks? That tells us it's doing a great job exploring the entire landscape, giving us a full, accurate picture. But, and this is a big but, if you get the settings wrong, say your steps are too tiny, you get this. The walker finds one peak and just gets stuck there, pacing back and forth. It never discovers that whole other part of the landscape. And that means your final map is biased, incomplete, and frankly, pretty useless. So how you design the random walk matters a lot. Okay, let's take a breath. We've gone from throwing darts at a weird blob all the way to a smart robot vacuum mapping invisible landscapes. So, what's the big deal? Why does any of this actually matter? Why should you care about any of these abstract ideas? Well, because this ability to explore the unknown just by using randomness has pretty much changed everything in modern science and tech. Look, this stuff isn't just some dusty academic theory. These methods are the engine behind modern AI. They're used to forecast the stock market, to build climate models, to simulate things in physics we can't build. They're critical for developing new drugs, and they're even used to create the stunningly realistic lighting you see in movies and video games. They are literally everywhere, quietly solving problems that used to be unsolvable. And the crazy thing is, all of that, all those revolutionary applications, it all boils down to this one simple idea we started with. At the end of the day, we're just taking the average of a random sample to get a good guess of a much bigger, more complicated truth. So it leaves you with this kind of wild thought, right? In a world that's always chasing precision and perfect answers, maybe, just maybe, the most powerful tool we have for making new discoveries is simply learning how to embrace a little bit of randomness. Something to chew on,